here. We are here right now. Welcome, beloved siblings. We are the Chicago Brain Buddies. We believe that by studying the brain, we can better understand human behavior and thus be more forgiving people and thus be happier. That there next to me is the one and only Professor Peggy Mason, Professor of Neurobiology at the University of Chicago. Hi, Peggy.
Hi there.
I'm Aaron Freeman.
What happened to your wingback chair, man?
The dog is downstairs, and I worry what the dog gets too excited.
The dog has the wingback chair, and you don't.
Well, but let me tell you this: I've actually scienced that wingback chair and the whole history of the wingback chair and what its original use was and how the French mucked about with it. Very interesting stuff. I'm going to do a video about it. But that's not why we are here today.
You're leaving me hanging, man.
Huh?
You're leaving me hanging.
That's so you'll watch Excitable Ape and Sciencing Today, and you'll see all the new stuff. But anyway, May is National Mental Health Awareness Month, and as such, we are going to bring a neurobiological take on mental health and how it is tested for. Fair?
Yeah. So mental health is a topic that touches essentially everybody, and I can't think of somebody who hasn't experienced either a mental health issue themselves or one in a loved one or a friend. I
think the number 16% of Americans will be diagnosed with major depressive disorder in their lifetime.
Yeah, and those 16% of people are related to or friends with everybody. Yeah.
Yeah.
So this is a really, really important issue, and
that we all get depressed, but we're not talking about the kind of depression that I get when the Cubs lose, or even if Sharon says something that hurts my feelings. We're not talking that kind of depression.
Right. We're talking about something which doesn't have a firm boundary or not firm boundary that I know of, but a very serious clinical condition that prevents an individual from pursuing a happy life.
And it makes it harder.
This is a big deal, and there are many strategies to combat it. One really effective strategy is cognitive behavioral therapy. There's nothing you really cannot say enough about CBT or cognitive behavioral therapy. It's amazing how efficacious that is.
And it has been shown effective to a large number of decibel points. There have been lots of studies.
It is really, I don't know if I don't think people consider it the gold standard, but I personally would think it's an arguable point that should be the gold standard.
And I believe
it's very effective.
I believe that CBT is a Chicago creation. Wasn't that Aaron Beck at Northwestern? I think it was.
Got me there.
Yeah.
So, anyway, but oftentimes people feel that they need or opt to use something besides or in addition to cognitive behavioral therapy, and they opt to use medications. So we don't really want to do experiments on people. We really want to figure out whether if I give a clinically depressed person this drug will this drug help a person that's clinically depressed? And so if we can't do experiments on humans, what do? Well, we do experiments on non-human animals, principally on rodents. So how are we going to figure out whether something is going to work in a human by looking at rodents? And so this brings us to this concept of validity. And validity comes in a number of varieties, but we're going to talk about 3 types.
Okay, now when we say validity, how are we defining that? That's a technical term.
We're going to talk about 3 types of validity. The first one is face validity. I look at that rat, and that rat looks depressed to me. Okay? Now let's make an analogy. When you watch a movie, and it takes place at some famous location, let's say the White House. What happens? Is it filmed at the White House? Well, no, it's filmed at a Hollywood set where they have recreated the White House.
A laboratory setting.
I personally, I don't know, have you watched White House Down?
No. I've watched The West Wing.
Okay, I haven't watched West Wing, but same deal. These are made to imitate, the sets are made to imitate the White House. There's an Oval Office. Yes. There's a portico. There's an outside exterior. And they look kind of convincing. That's face validity.
Got it.
Now, if you go into the door, if you open that door at the Hollywood set, are you going to come to the same series of rooms? Are you going to get to the China room and the blah, blah, blah room and all that when you go step in? No, because you're only going to get to the rooms that the Hollywood set has built. So while this...
the set has face validity, but it's not really.
Not construct validity.
Construct validity,
not construct validity. And so in the terms of depression, you could say, okay, that animal is not moving. It's sleeping all the time. It's not eating much. It looks depressed. But in fact, what's wrong with it is it's paralyzed. I don't know, something else, something that's not depression. That would be face validity without construct validity. And the problem is that in general, rats and mice are not humans, rats aren't mice, rats aren't humans, etc. So we can't just automatically assume that the same processes are giving rise to this depressive, this on the face of it, depressive-like behavior in the rodent as would as occur in the human.
And it's important that we want to understand that this rodent is in fact depressed, because we want to try to experiment with various medications on the rodent and see how that affects.
Well, actually, the construct validity is going to allow us to understand what happens in depression, and to think about new ways that we could combat it.
But when we talk about validity, you're talking about how valid is this model?
How mechanistically similar is the model to the human?
Yes. Okay. Yeah.
How valid is it? Processes happening in this rat that looks lethargic and not interested in life as happen in a clinically depressed human?
Got it.
The answer can be some degree of yes, but in the end is never going to be 100% yes.
Okay.
So, but then you mentioned something else. What do we want to do? We do want to understand it, but we also want to treat it.
Right.
And so that's a different type of validity. That's a validity that we call predictive validity. Okay. So can we predict the efficacy of some intervention by using this model, even if the mechanisms aren't identical? Can we still use it to predict how well a medication will work in the human?
So that if you get an antidepressant that appears to relieve the depression in a mouse or a rat, how well does the administration of the alleviation of that symptom in a mouse predict the alleviation of a similar symptom in a human?
The symptom of interest in the human, which is clinical depression.
Yeah.
So great. So that's what we want to do. Now, there are a couple of places where this has been, there's a couple of places that we have decided to talk about in this iteration of Chicago Brain Buddies.
Because it's Mental Health Awareness Month.
Before we get to mental health, let's talk about a really simple one, something called the tail flick test. Okay, now this is what happens in a tail flick test is here's a rat and it's got a tail. Actually, I have a rat somewhere around here. Here's my rat.
Oh, good.
Here's my little rat. Okay, here's my rat. Here's my tail, the rat's tail. And I'm going to shine a little light bulb on the tail. And when this tail heats up enough, the rat's going to do this. It's going to whip this away. Whoop. It's going to flick its tail away from the hot.
That's not actually a stuffed rat, is it? It's not some laboratory some experimental rat that you just kept around.
This is very polyester. Very polyester.
Okay. No rats were harmed in the making of this prop.
And here we have a different rat. I have rats from a variety of different cultures. This is made out of, I don't know, something.
That looks like it's
And
made
we
out
have,
of
we're not done yet. We
Okay.
also have this this rat. Again, I think we're talking polyester.
Okay.
But in any case, the tail flick test is this. It's going to flick its tail away. Okay,
So
now.
So that's a pain test, right? So
That is a pain test.
It flicks its tail away when it gets uncomfortably hot.
When the rat is free to flick or not flick.
Right.
Okay.
But it will
so
flick.
when it decides, when it's had enough, it flicks. Now, let's say I gave that rat morphine.
Okay.
Now what is our little rat going to do?
My guess is it's going to be a lot or some significantly longer period of time in the heat before the tail flicks.
Exactly so. And so in fact, it will spend ridiculous amounts of time on the heat. So we decide, okay, we're going to take care of you. We don't want you to get injured. So we'll cut the heat off at some number of seconds so you don't get damaged.
Right.
Okay. So that is an example of it is predictive of human post-operative analgesia. In other words, post-operative relief of pain.
So if you give morphine to the rat and the rat can endure more pain without moving its tail, then that is predictive of the effect that morphine will have on a human in pain.
Right. And this is not useful for morphine. We know morphine's a great analgesic. So it is predictive for new analgesics. Analgesics that we want to use that might do better than morphine in a variety of ways, such as not exhibit tolerance, not have an addictive possibility, etc. So there are ways in which we could do better, or there are ways that we imagine and hope that we can do better than narcotics to relieve pain. But to do that, to figure out what those drugs are, we need a test. And the first go is the first thing that those compounds have to pass is that they have to be able to suppress this.
Okay.
Now, we have a few comments. That rat looks suppressed.
It's not an optimistic rat.
Sharon likes the naughty rat.
Well, that rat looks like it's made out of marijuana buds.
What's that?
The rat looks like it's made out of marijuana buds.
Okay. I'll take
it. Looks like flower tops. That's flower top rat when I tell the story. Anyway, go ahead.
Okay.
So now, we know that some drugs have predictability. They have predictive validity. They can.
So what is that good for? Is it good to relieve somebody who has what we call a neuropathic pain, a really long-standing pain that there's no physical injury associated with? And the answer is no. This is the tail flick test is very useful for a particular type of pain, an acute pain, most commonly used for post-operative pain. The pain that you get because a surgeon incised your skin.
So they
hurts.
So they use the tail flick test to test the efficacy of analgesics.
For post-operative pain.
Specifically for that. Okay.
Right.
Got it.
So that's an example of an animal model. It has some face validity in the sense that the rat flicking its tail is not that different from a person putting their hand on a hot stove and doing this. They're both withdrawals. So they have a tail and we don't have a tail, but those are details.
But you can look at the rat and say, oh, I think this rat is too hot. Similarly, you can look at a human being putting their hand over a fire and say, oh, I think this person sensed that fire was too hot.
Yeah. And so they have a little bit of face validity. They have some constructive validity in the sense that the neural pathways involved are very similar. But what they really have is predictive validity, and it's easy and cheap. So drug companies love this.
Okay.
Okay, so now let's move over into mental health land.
Okay.
You think there's anything as easy and cheap as the tail flick test?
Yes.
What is it?
Yes. The forced swimming test.
Okay, tell me about the forced swimming test.
So they make the they make
this
a rat.
This is sad, by the way. I'm just going to warn people.
Yes. Okay.
Sad. I don't do this. I don't like it. It's sad.
Okay.
I like my rats. I like my rats to have a good time. Okay, go ahead.
Look, this is not the institutional review boards around the country have approved the forced swimming test. Fair?
No, forced swim test would be, there are two different types of approvals, and this would be approved by the Institutional Animal Care and Use Committee, the IACUC.
Okay, fair enough. Fair enough.
Okay.
So they have a little cylinder, glass cylinder filled with water. You put the rat in. If the rat swims around, it's not depressed. If the rat stops swimming, we say it's depressed. And they use that the length of time that the rat will keep swimming is a measure of its depression, and an antidepressant drug, an effective antidepressant drug, will keep the rat swimming for longer.
Correct. Right. Okay. So they're all going to give up at some point.
Right. But the rat will swim for longer. At some point
because there is no point. There is no platform. There's nothing.
And there's one other test that is less kind, which is the tail suspension test.
Nah, people aren't using that.
Well, there's certainly videos of people, experimenters.
Let's keep to the forced swim test. So the forced swim test, the longer they swim, the less it is interpreted as the less depressed they are. The shorter they swim,
the more depressed.
But then you give them these drugs and they'll swim for a longer time.
Right.
And this has predictive validity for antidepressant action.
Right. Now, so how this is directly analogous from a rodent to a human? The same drugs that work for humans will work for rats and vice versa?
Well, I mean, it has predictive validity. That doesn't mean 100%.
Okay. Yeah.
It's not 100% situation. Gravity kind of is a law, but other than that, we don't do too many 100%.
But there's also a thing that you noticed in your rats, I think, which is learned helplessness is another version, a sort of depression, to the extent that the rodent becomes immobile.
Right, so they give up. They give up. They realize that there's absolutely nothing else that they can do. And Sharon makes a good point. I would just want to point out a comment that Sharon just added, which is that once they give up, they don't drown. Let's not get this is maudlin. It has its maudlin aspects, but it's not that bad. They don't drown. They just float.
Yeah.
So they're not happy, but they've given up trying to find a better place. They've given up trying to find the grass is greener somewhere else.
Right.
But they're not drowning. They're floating.
So now, what do we know about the neurobiology of depression itself?
So we know quite a bit about it. It's not my exact field, but we know that for example, the prefrontal cortex is very involved, and we know that there's a dysregulation of a lot of processes that should be working that aren't working in the depressed individual. Besides the forced swim test, there was a test a long time ago that was invented by Lou Seiden, who was a professor here at University of Chicago. And the basic idea is very similar to the forced swim test. It is that you can press a lever to get something good, okay? So let's say you're going to press a lever and get a little bit of sugar. And now I say, okay, you got to press the lever, let's say 3 times. So you press the lever 3 times. But now after you press the lever 3 times, you have to take a time out. You have to wait before you press it again.
Okay.
Okay? The animals that can't wait are the ones that look depressed. And if you can give a drug that allows them to wait for a longer amount of time, a longer time out before they press again, those drugs tend to work as antidepressants in humans.
So this has to do with
same principle.
This has to do with the ability to delay gratification.
Right. Which is why when we were talking about this earlier this week, I was thinking about the marshmallows.
The very, 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 very famous marshmallow test. Can you tell us quickly what that is?
Well, why don't you tell us the marshmallow test?
So the marshmallow test was a very cruel, now talk about cruel. This was a cruel experiment. They would put the kid, take a little 5-year-old kid, put him in the room with a marshmallow, say, okay, now you sit right here. If you don't eat this marshmallow for 15 minutes, was 15 or 5? I forget, some period of time. If you don't eat this marshmallow, I will come back and you'll have 2 marshmallows. And then they leave, and you see that I'll put a link to it later on in this video. But you can see these poor kids like looking at the marshmallow, and then some kid will like just touch the marshmallow, and some kid will put it up to their nose. But long story short, they followed the kids who took this test over decades, and it turned out that the kids who were able to delay their gratification and not eat the marshmallow had better jobs, did better in school, had more success in their families, and the kids who could not delay gratification were more likely to be incarcerated, more likely to have drug problems, that there was a huge cornucopia of behaviors that were predicted simply by whether or not you could delay gratification in eating a marshmallow.
Right.
Is that fair?
Yeah. Yeah. And so what it is a really good, crude but good test of self-regulation, the ability to control oneself, to regulate one's own desires and take a pause.
Well, now, so Alani asked an interesting question. If brains are supposed to keep us alive, then how is it that our brains have these mechanisms that will make us miserable?
Well, so I mean, we have to have negative emotions. Just as we want to have if I through evolutionary time, I'm an animal, I want to have positive emotions about finding food, finding water, finding warm places to sleep, and finding mates and friends. We're social beings. And I want to have negative emotions when I encounter some nasty critter that wants to bite me, or some place where I get stuck and I fall. So negative emotions are just as important as positive emotions. There's no question. But the way I think about life is you're always walking that razor edge between a little bit too much negativity, a little bit, it's a tough life.
But some people, you mentioned us being social animals, and I've certainly read that one of the usefulnesses of negative emotions is that it lets our troop mates know that we need help. That when we appear sad, it lets people know that, hey, give this ape needs a hug.
Well, I think that that's a lofty thing, but even before you get to that my friend over there looks really worried. I should probably be worried too, because something's bad coming down the line.
Yeah.
Right.
Yeah.
My cat gets a big puffy tail. I look at the other cat. They're gonna have a big puffy. They're very interested in why their sister is alarmed, and that's a very useful thing. Yeah. So, Adil is asking about the significance of experimenting on rats to predict antidepressant action in humans. And that's the critical question, Adil. That's what predictive validity is all about. And so it just so happens that occasionally we happen upon a pretty good, what people call animal model, and I call a non-human animal model of some human condition that predicts pretty well for humans.
But let me say, though, as I understand it, it's tricky to tell, for example, what is depression, to distinguish what's depression in a rat from what's schizophrenia in a rat from what's anxiety in a rat. While so that their behaviors, there's face validity, that may appear to be present, but really it's much more subtle, and you can't really make you can't interrogate a rat the way you can interrogate a human to find out as specifically as you might like to.
Right. And the genetics is coming out that the same variants are leading to a susceptibility to, say, both depression and bipolar disorder. So the categories that we've set up in humans may not be exactly biologically accurate. I think that is bound to be true. And so what can we learn about the neurology of humans from studying rats? We can learn a lot. It's a lot closer when it comes to, say, pain processing than when it comes to attention. So our ability to predict ADHD drugs is less than our ability to predict analgesics.
Well, Luani makes another interesting point, is that in certain ways, our brains do respond the same way to emotional distress or emotional danger as to physical danger.
I think that's true. I also have to point, my sister-in-law says the brain is the most important organ in the body, according to the brain. That's true. That's true. So, big caveat there.
Yeah, that's true. Well, I mean, of course, that's always the caveat with every kind of science, that even though there are amazing things we can do and amazing drugs and amazing technologies, we still really don't know what only 5% of the oceans have been explored. 5% of known space can be explained by physics, and I don't know what percentage of the brain we understand, but it's not.
Yeah, but I mean, with the brain, you have this particular problem that it's the brain investigating the brain.
Well, there's that too. Yes.
And we don't really allow that in science, but we've taken a pass on that problem in neuroscience because we have no choice.
Right. Yeah. But Lonnie was saying, though, that it is interesting that brains don't necessarily distinguish, or areas of the brain don't necessarily distinguish between physical threats, physical pain, and psychological or emotional or social pain.
I mean, related to that, I think one of the things that we've learned, William James certainly knew this, and then we've learned it more recently again, is that brains don't particularly separate beautifully between self and other. So if I think about, in this regard, I think about Hurricane Katrina, where people were offered to be rescued, but if they couldn't take their pet with them, they didn't want to be rescued. So that other being is so much a part of themselves that there's no effective separation.
Well, now, it's interesting because people talk about that soldiers don't fight for their flag or the country, they fight for the people in the unit. And John McCain, when he was a prisoner of war, was offered release because he was an officer, and he refused it. He would not, he chose to stay and be tortured in a prisoner of war camp rather than use his privilege as an officer to get a better fate. So just to your point, that we don't, there are parts of our brains that don't distinguish between us, or that feel so connected to others, that we would just as soon suffer.
Right. And so it's a neurobiological confirmation of a William James concept of the extended self. So William James included not only the other beings that you care as much about as you do about yourself, but the things that you care. If the building you're in goes up on fire right now, what do you take? What do you take right now? That is probably part of your extended self. So yeah.
Yeah. Well, okay. So to come close to wrapping this bad boy up here. So the good news is that we really can learn and experiment on analgesics and various drugs that'll help people without actually experimenting on people. That the rodent model genuinely is, and we continue to get better at it. I assume we continue to understand rodent physiology and rodent behavior better. Is that right?
More and more rodent models of human conditions are being developed, but this is an ongoing process that needs more and more help.
But The rats are helping. Your little buddies, your little rat pals are out there doing their little ratty work, helping to make us humans healthier and happier. The woman with the rats is Professor Peggy Mason, Professor of Neurobiology, and a very dignified person, a very serious and dignified scientist at the University of Chicago. I'm Aaron Freeman, artist in residence for the Chicago Council on Science and Technology. We're here every Thursday, and boy, we're sure glad that you guys joined us and watched us, and we hope that you will go to, we certainly think that you should check out www.thebrainissocool.com. Thebrainissocool.com, the blog of the fabulous Peggy Mason, and you can find us on YouTube and, of course, right here on Facebook. So thank you, Peggy.
Bye, everybody. We love you.
We love you. See you soon.